Section 4.1 is polynomial functions. I would pause the video and write down these notes. So a polynomial function is anything of this form right here, no fractions, no negative exponents, no square roots. The degree of the polynomial is whatever the highest power is, and we call something that is just a monomial like this a power function. And that decides what the end behavior, so really, really big values of x, is it going up or is it going down in the positive and negative directions? So real quick, what I want you to do is I want you to pause the video and graph these four functions with your graphing calculator and take note of the different end behaviors. What happens as x's get really big in either the positive or negative directions? So here's a little graphic organizer about end behavior. So if n, the degree of the polynomial, is even, then the ends end in the same direction. The middle, different things can be happening in here depending on the polynomial. But if n is even, so you have an even degree polynomial, your ends are going to end in the same direction. If n is odd, O goes with O, your ends are going to end in opposite directions. Odd is for opposite. So like an x cubed here, or a negative x cubed versus an x squared or an x to the fourth. Your leading coefficient, if a is positive, it's happy, it's going to end up in the positive. So if it's positive, it's going to end in the positives. If it's negative, if your leading coefficient is negative, it's sad, it's going to end down in the negatives. So even, same direction, odd, opposite direction. A positive, you end in the positives. A negative, you end in the negatives. Multiplicity is the power a zero or a factor of a polynomial is raised to. So if you have a polynomial in factored form like this one here, then whatever its power is its multiplicity. So reading off of this, I want you to pause the video and find all the zeros of this polynomial and what the multiplicity or what power each one is raised to. So degree and your a value is telling what's happening in the end behavior. Multiplicity is telling us what's happening at each of these zeros. So we have a zero of x equals 2, x equals -1, and x equals 1/2. This first one, we don't write it. There's an invisible 1 here, so it has a multiplicity of 1. This second one, x equals -1, has a multiplicity of 2, and this third one has a multiplicity of 3. So what does the multiplicity mean? The multiplicity is telling you what's happening on the polynomial at that specific zero. So if you have an odd multiplicity like x equals 2 or x equals 1/2, then the polynomial is going to actually cross the x-axis at that point. For a multiplicity of 2, or an even multiplicity, it's going to touch. So think of a parabola as x squared, it's even, it touches, comes back down, and goes up. Versus an odd, like x cubed, actually crosses the x-axis at that curve. So odd crosses, even touches. So now we're going to use that information to help us graph this one, x squared times x minus 2. So whenever you're given a polynomial, you want to make sure it's in factored form first. That's the only way at this point that we're going to be able to graph them. This is already in factored form. So the first thing I want you to do is pause the video and find the zeros and the multiplicity of each of those zeros. So we have two zeros. The first one, x squared, 0 makes that 0, and it has a multiplicity of 2. I always tell myself, okay, is that going to be a touch or a cross so I don't forget later on? So that means it's going to touch at x equals 0. Here I have x equals 2 with a multiplicity. If it's not written, that means it's a 1. That's an odd multiplicity, so it's going to cross. So now we know what's happening at each of the zeros. Now we need to know end behavior. So first we have to find the degree. So when it's in factored form, the way you find the degree is you add up all of the powers of the factors. So in this case I have a 2 plus 1. My degree is 3. So I want to remind myself, okay, that's odd, which means they're going to end in opposite directions. And my leading coefficient is 1, which means it's positive, so that's going to end up. So now if I graph that, I'm going to put all that information together. So I have a 0 at 0 and a 0 at 2. This is as detailed as the graph needs to be. Make sure you do label your x-intercepts, but that's about it. So on this one, I knew I had to touch at 0 and I had to cross at 2. I want to end up, and because it's odd, I need to start. That means I need to start down. So I'm going to start down, touch at 0, come back down, and then cross at 2. So I'm touching at x equals 0, I'm crossing at x equals 2. It's odd, that means they end in opposite directions, which I have, and a is positive, so I have to end up. So now let's try this one. First thing I notice is not in factored form, so I need to put it in factored form first. First thing I notice is that I can factor out an x squared out of everything, and then I'm left with x squared minus 2x minus 8. And that's a quadratic trinomial, so that will factor. So go ahead and pause the video and finish factoring this, and then find all the zeros and their multiplicities. So factoring this, x squared minus 2x minus 8 factors into x minus 4 times x plus 2. So then my zeros end up being x equals 0 with a multiplicity of 2, which means it's going to touch. That's from this x squared. X equals 4 from this x minus 4 factor. It has a multiplicity of 1, which means it's going to cross the x-axis there. And x equals negative 2 from this x plus 2, multiplicity of 1, so it's going to cross. So now what I want you guys to do, you need to find the degree and find the sign of a, whether it's positive or negative, to be able to find in behavior, and then graph this polynomial. So if you add up all the multiplicities or add up all the powers of your factors over here, you end up with a 4. So you have a degree 4, which means it's even, so they're going to end in the same direction, either both up or both down. A is a 1, so that means it's positive, so that means you're going to end up. So since it's even and you're going to end up, you're also going to start up. So I'm going to start up. As I come to negative 2, I'm going to cross it because it has an odd multiplicity. As I come back to 0, I'm going to just touch because it has an even multiplicity. And I come up to positive 4, I'm going to cross because it has an odd multiplicity. So this is what the graph of that polynomial looks like. Here we have an example of modeling with a polynomial function. So we're comparing the number of Cavaliers, it's the type of car, produced versus their cost, or how much it costs to produce it. So first thing, normally we're going to do a scatter diagram. Because of room on my screen, I'm going to wait for that and skip straight to part B, finding the average rate of change of cost from 4 to 5 Cavaliers. So if they were to only make 4 Cavaliers versus if they were to make 5 Cavaliers, what would the difference in price be? So I want you to pause the video and do part B, and then also do part C. So for part B, average rate of change, that's slope, change in y over change in x. So 50 minus 43 over 5 minus 4. These costs are in thousands of dollars, so it ends up being $7,000 per car. So it costs an extra $7,000 per car at this point. Part C, you want to find the average rate of change between 8 and 9 cars. So same thing, average rate of change in y over change in x, 105 minus 85 over 9 minus 8. At this point, it now costs an extra $20,000 per car for these Cavaliers to be manufactured. So the first question we need to ask ourselves is this going to be a linear relationship? If this average rate of change was 7,000 and this one was 20,000, that's not constant. The definition of a linear function is a constant average rate of change. This is not constant. So now let's move on to part A and part D, which is creating a scatter plot and then using a graphing calculator to find the line of best fit. So using your Desmos, create a scatter plot using this table. So here's the scatter plot that Desmos did for me. As you can tell, it's not quite linear. It does have an odd degree because it ends in opposite directions, and so that's probably why it wants us to do a cubic line of best fit. So now going back into your TI graphing calculator or Desmos, go ahead and find the cubic line of best fit for this and graph it on the same screen as your scatter plot. So here's the cubic function it gave me. You can see down here A, B, C, and D for your cubic function. And now we're going to use that to extrapolate our data and predict how much it would cost to manufacture 11 Cavaliers. So go ahead and pause the video. Use your given line of best fit to extrapolate this data. So if you plug in 11 into your cubic function of best fit, you end up with $170,010. So that's the cost of producing 11 Cavaliers per hour based off of the data that we're given. So now the last part, I want you to think about what the Y-intercept means. So at x equals 0, or at 0 Cavaliers produced per hour, it still costs the company $10,000. So I kind of want you to think about that on your own. Why is that? What does it mean in the real world situation as we talk about this modeling stuff? So remember, when you're graphing polynomial functions, it has to be in factored form first, and then you want to look at the zeros and the multiplicity to see what's happening in the middle of the function, and the degree and the sign of a to see what's happening on your end behavior or the very ends of the function.